Hello, my name is Max Green. Today I'll be presenting simultaneous trajectory tracking control and online mass estimation for a regolith excavating robot via integral concurrent learning. The authors on this paper are myself, Michael Dupuy, Joe Cloud, and Warren Dixon. Here's an outline of today's presentation. First, I'll discuss regolith excavation, discuss our robot dynamics, talk about how we can use integral concurrent learning to perform online system identification, discuss our stability analysis that proves convergence of our mass estimation, and finish the presentation with the simulation results. The desire to perform regolith excavation comes from the need to perform ISRU on other celestial bodies, such as the Moon or Mars. It's not desirable to bring additional resources like fuel, water, or to bring pre-constructed structures onto the surfaces of other celestial bodies. Therefore, ISRU focuses on the utilization of other local materials such as regolith or plastics. These local materials can then be used to produce additional fuel, water, or structures on the surface of the bodies without the need for expensive transportation costs. Here you can see a picture of the Regolith Advanced Surface Systems Operation Robot, or RASSOR for short, playing in the sand. RASSOR is used to manipulate, excavate, acquire, haul, and dump regolith around on other celestial bodies, such as the Moon. While RASSOR is an advanced excavation robot, unfortunately it doesn't have sensors to directly measure the mass of the excavated regolith on board. In this paper, our objective is to indirectly estimate the amount of mass that has been excavated by RASSOR online. This objective is completed by using an adaptive control-based online system identifier in which the bucket drum excavator and lifting arm are excited. In doing so, the mass of the bucket drum excavator containing regolith can be estimated online. Since the mass of the bucket drum excavator is a known quantity, therefore, we can use our estimate to determine the mass of the excavated regolith. We're motivated to do adaptive control techniques applied to this problem because we know that we can use the dynamics and motion of the robot to determine unknown parameters such as mass online. And if we can determine the mass of the lifting arm and bucket drum excavator, similarly, we can figure out the mass of the excavated regolith. You may wonder why we're using adaptive control techniques as opposed to simply static measurements in which we lift up the arm and take the weight of the bucket drum excavator with and without regolith. Well, that's because that technique relies on calibration curves that were set pre-launch on our mobile robot, so it doesn't deal with the uncertain environments that we may face on different celestial bodies. There's multiple points of failure. RASSOR's dynamics can be described by the Euler-Lagrange equation at the top. However, many parameters in the equation are unknown a priori or unmeasurable. Explicitly, the control input, which is the torque applied to each joint, is known. We also assume that the joint position and velocities are measurable, but we can't measure the joint acceleration. Furthermore, we don't know many of the parametric constants, such as terms in the mass and Coriolis matrices or friction effects. The Euler-Lagrange robot dynamics are linearly parameterizable, meaning that they can be written in the form y, which is a known regression matrix, times theta, which is a column vector of unknown parameters. While the regression matrix y is measurable, theta is neither measurable nor known a priori. Therefore, in the control system development, we approximate theta with theta hat, which is our real-time estimate. In essence, what we do with integral concurrent learning to approximate theta online is we relate the left-hand side of the dynamics to the right-hand side of the dynamics to solve for theta. However, y is a function of q double dot, so therefore to remove the need to measure or compute the second derivative of q, which we don't have a sensor for, we take the integral of both sides and compare them. To facilitate the control development, we define R, which is an auxiliary error signal that is proportional and derivative of the error. The controller is designed using a new regression matrix, Y2, an estimate of the unknown parameters, and two error signals, the actual error and the auxiliary error. At the bottom, you can see two equivalent representations of integral concurrent learning. The top one is an implementable form, meaning this is what we would actually implement on the hardware, whereas the bottom equation, the analytical form, is what we used in the Lyapunov-based analysis to guarantee parameter convergence. The assumption associated with integral concurrent learning is called the finite excitation assumption. Finite excitation assumption says that once the system is sufficiently excited over a finite duration of time, capital T, that the summation term with script y transpose times y is full rank, at which point this assumption condition is met. To prove boundedness and convergence properties of our error system, our controller, and parameter estimation errors, a Lyapunov-based stability analysis is performed. Using the finite excitation assumption, we can show that our error system and parameter estimation errors exponentially converge in finite time. To show the performance of our developed technique, we perform a simulation. In our simulation, we pick up 3 kilograms of regolith, and the parameters of the lifting arm and barrel drum excavator are shown on the right there. So our Lyapunov analysis shows that we'll be able to exponentially estimate the M2 term, which is the sum of the excavator and regolith masses. So once we determine M2 online, we can subtract the mass of the excavator, and therefore we have an estimate of the regolith only. On the left, there is a video showing the position of the arms during system identification. Note that there's not that much wiggle. The arms aren't moving significantly, because if you move them a lot, then the regolith would shift inside of the barrel drum excavator and would provide a bad estimation, most likely. Then on the right, we can show the real-time regolith mass estimate. So within about 5 seconds, our estimate converges to the actual value, and the simulation shows that we can successfully estimate the mass online. In conclusion, in this paper, we develop an integral concurrent learning based adaptation law, and we use this adaptation law, which achieves exponential convergence, to determine the mass excavated by the RASSOR robot in finite time. So the next steps of this project are to actually apply this technique to hardware or in high fidelity simulation. Thank you for attending my talk. At this time, I'll take any questions.